Hey students, I got a question here on the real hard one. I think this is the hardest one, definitely involving some calculus. It's from the harder book here. And let's see if we can work this one out here together. It says the accompanying figure shows a flat, infinitely long sheet of width A. So kind of looking at this like long sheet, if you will. I guess it'd be a little bit like taking one of these stickies, if you will, and maybe I'll make it kind of smaller, something like this. Okay. And so this is a flat sheet. It's really, really long this way, but only has a width of A in this direction. So there is A. So it's infinitely long sheet of width A and carries a current I that is uniformly distributed. So in other words, we have a current carrying device. It's not round. It probably is this metal connector. Usually in electronics, this is probably connecting pieces together, so we refer to it as a bus. And so this is an electronic bus, if you will, and the current goes through, this end here, and it's spread out. So it's not spread out in a circle like a wire would be, but it's spread out in a small rectangle that has a length of A and a thickness that they don't really describe, and we'll just say it's thin for now. It says find the magnetic field at the point P, which is in the plane of the sheet and is a distance x from the edge. Now, they don't really put it in the picture, but I'll put it right there. They're saying this is x. So in other words, if I have this sheet here, I'll just put it kind of next to it, we would be looking at some point P here, a distance x away from the edge. Find the magnetic field at point P, which is in the plane of the sheet, and a distance x from the edge. And then test your result in the limit that A goes to 0. Now, the idea there, if you can kind of imagine, if this got thinner and thinner, then you would just have kind of this long, thin wire. So in other words, this last part says that if you take the limit as A goes to 0, you should be looking at the magnetic field from just a long, straight wire. And in fact, that's kind of our clue to how we're going to do this problem. Because I'm going to do this problem kind of in the reverse of what they say to test it. I'm going to view this as a whole set of thin wires next to each other and add it up. In fact, I grabbed some pencils that I thought might help us visualize this better. But if I put a bunch of pencils together, you might think of this whole set of pencils as being this sheet. And so this whole set of pencils has a width of A, and they're really long this way. And we're trying to find the magnetic field over here at point P, a distance x from this edge. And we don't have anything like that in the book. I mean, we had the geometry of a wire, we had the geometry of a loop, but we didn't have anything geometry like this. So let's break this down into the geometry that we do know, and that's why I think these pencils are helpful. What you can do is think about how much magnetic field would you get from just that one pencil. That's just a wire. And then add it to the magnetic field you would get from this pencil, a second wire right next to it. And then the magnetic field you'd get from a third wire, and then the magnetic field from a fourth wire, and then a fifth wire, sixth wire. And since we know calculus, what we could do is think of these wires as being infinitely thin and then we have an infinite number of them. So we're going to add up a number of infinitely thin, but an infinitely number of them so that we can get a width of A. So that's kind of my strategy. And I say that's my strategy because, again, going back to your textbook, and this time I printed up the correct figure. If any of you watched my last video on number 65, I accidentally printed the wrong equation. But getting the magnetic field from a straight wire has already been done for us. We can get its magnitude with this equation, and we can get its direction from the right-hand rule. So, again, kind of repeating the right-hand rule, or maybe guiding you back to number 65 if you haven't done that. You want to imagine grabbing the wire with your right hand, not your left, with your thumb in the direction of the current, not the opposite direction, and then your fingers curl around, thinking of the tips of your fingers as little pointers in something that looks like this. And so that's how we get the direction. So if we come back to our problem at hand, and we kind of set up our pencils here, if we ignore all the other pencils and just look at this first one, and imagine grabbing it with our right hand with our thumb in the direction of the current, the magnetic field would go in a circle around it, kind of like this picture with the currents pointing down like that. And so that means this point P would have the magnetic field, if I maybe grab my green for the field, as pointing, and put a little dot, up towards you, or out towards you on the screen. And so here's my right hand, I'm grabbing it, and it's pointing out. And the second wire right here, if I imagine grabbing that, now it's a little further away, so because of that, I think the field at point P is going to be a little weaker, but the direction is still out of the screen. And number 3, kind of that same comment can be made. Number 3 is a little bit further away than number 1, and a little bit further away than number 2. And so the field at point P is a little weaker from number 3 compared to number 1 or number 2. But its direction is still out. And so if I only focus for a moment on the direction, and I think about adding an infinite number, they're all going to be pointing out of the screen. And so I guess the good news is when we add up vectors and they're all in the same direction, it's really nice, because something that has a magnitude of 3 and another vector that has a magnitude of 4 means you can just go 3 plus 4. And if the next one has a 5, then you can just go plus 5. There's no sines or cosines. There's no x component. There's no y components. So in that sense, the problem is easy. Now, it's still overall a hard problem. But in the sense of the direction, and in fact, maybe you did see the one I just did on number 65. And on number 65, we had the vectors in different directions, and we had to give that some thought. Fortunately, we had some symmetry, and so if you got a chance to see it, you'll notice that I put 1 and 2, and noticed that as I thought about the x components, they canceled off, and y components added together, so I just had to double them. And so there was things nice about the x and y components, but I had to give that a lot of thought. Here, fortunately, I don't have to give it a lot of thought. They're all going to be, towards the screen. We usually call that the z direction. And so I guess what I can say right away then is when they ask for find the magnetic field at point P, I can say already that it's going to be, up out of the plane. And so, again, if we're thinking of this little sheet of being the plane of the screen, then this point P, I'll put it right there, this point P is in the, out of the screen. So it's in the Z direction. So that's probably the easier part of it, the fact that we know the direction right away. And the fact that they're in the same direction means my math's going to be a little bit easier. However, given I have an infinite number of them, that's going to make my math a little bit more challenging here. All right, so let's do this for a moment. Let's just take a little tiny section here right next to it. So in my analogy of my pencils here, this would be this first pencil. And so if I look at this first pencil, I can think of it as just a wire. And as I said a moment ago, this would be the magnetic field from just that one by itself. So let me write down that equation here. So I'd say, okay, so a magnetic field would be mu naught times I over 2 pi r. Now, again, if I'm thinking about it as just this first one, I need to be a little careful. This I in that equation would not be the total current I that they put in the problem, because they said I is uniformly spread out. So in other words, I is the total current in all of these, not just this little microscopically thin one. So I might want to change this equation to something other than I. And noting that I'm probably going to, take a calculus approach and think of this then as chopped into an infinite number of really, really tiny, tiny pieces. I could say that the current in this first one is a really small amount of current. And so let me use the calculus notation di. Maybe a quick comment on our calculus is important. When you're doing an integral and you say, something dx, usually integral of f of x dx. Where that came from was really f of x times a small width of dx added together in the limit that delta x goes to 0. So this delta x represents a small little piece that's going to become infinitely small. That's why we like to use the dx to represent a infinitesimal piece of it. And then we would add it up. So I'm going to just do that right now. I'm going to say that little bit of current in this first one is di. Okay? And then that would be divided by 2 pi. And I guess technically it's x for the first wire. Right? Because, again, this first wire, let me just make sure I got the x right, is at a distance of x from the edge. Okay? So it's technically x. But as long as I'm here, let me go plus, I'll just put a little box, because I ultimately want to think about more than just the first wire. And so the second wire is going to be the x plus a little bit. And the next one is x plus a little bit more, and then a little bit more, and a little bit more. And so maybe I'll just put a box kind of with a question mark to say I need to give that some thought. But it's definitely just x for this first wire. So if I'm only thinking about the first wire, it would be x. Okay? And then over here, instead of calling it B, because B you might think of as the total field from the whole sheet, you might call that a small amount, an infinitesimal magnetic field, dB. So in other words, dB, a small amount of a magnetic field, is coming from a small amount of current that is a distance of, and for the first one is x, but they get further away. In fact, the last one, kind of think about adding a bunch of these. The last one would be way over here, and so it'd be x plus a. And so this number here, this box, is going to go from 0 to a for each wire. Okay, so that's going to be my variable as I add it up. Okay. Now, once I add them all up, I'm going to get the total field. And so I guess I would do it this way. How do I get the total field? I add up, I integrate. So remember, that's what an integral means, right? This an integral means the summation of some function added up. So if I add up all my dBs, so if I were to add up the magnetic field from each of these little tiny wires, and 6 of them, but really it's going to be an infinite number, I would get the total field. And of course, this was that nice comment earlier. I don't have to worry about the cosine or sine to get the x or y components. This is just going to add them up. So you might even say this is the total field in the z direction, because we get a magnetic field that is only in the z direction. And so we're just going to add up magnitudes. We don't have to worry about components at all. Okay, so let me write that as mu naught times a little bit of current in one of them, divided by 2 pi. Oh, and I'm still kind of left with this crazy thing. So x is the distance away plus some parameter that as I do my integral, it's going to keep getting bigger. The first time it's going to be 0, and the next time it's going to be 0 plus a microscopic amount, and then another microscopic amount. Eventually, it'll be a. Okay. So we're getting close. It would be nice, though, maybe to connect these together, and I would do something like this. The microscopic currents here is related to the total currents that's spread out over the whole width by something like this. And the key word right here is uniformly distributed. In other words, if you took the whole current I and divided it by its whole width A, you might think of that kind of like a density, where you take the, say you want to know the density of a chocolate in a chocolate bar. You might take the whole chocolate bar and divide it by the whole mass of the chocolate bar. Here, I could do a small piece, like a little bit of current, and that would be here, as long as I divide it by a little bit of a segment of this width. And so maybe it might be nice to call it a dW or something, a small little piece of the overall width of this strip. So you can do the whole current over the whole width, or that should be equal to a small amount of current on the same corresponding small amount of width. Now, here's why that's nice, is because I can now have a mathematical expression for how much current is in this microscopic piece. It's basically this number, which is the density, times how much width I have. And then that changes my integral from adding up currents to adding up widths. And that's then going to fit right in here perfectly. All right, so let me put all those words into my equation. Okay, so in place of the microscopic amount of currents, let me put I over A dW for the width, okay? And then divide it by 2 pi. And now x is the initial distance away. And if you think now as W as being a variable, starting at 0 and the width increases until I get to A, then this W symbol, the width symbol, is a variable for integration. Now, you're probably used to using your integrals as a dx instead of a dw. But a quick note here, I guess I wanted to stay away from that because the author gave us the x for a constant number, the edge to the, from the edge to the point P. It says the plane of the shape at a distance x from the edge. So I didn't want to add up along x because this would kind of imply that x is changing, and the distance to the microscopic currents is changing, yes. And so I need something that changes. And if I labeled that as an x, that you might confuse it with that x. So I don't know what was better, but I'll just pause here and say that's what was going into my head, that I want to do an integral. And part of me wanted to change this to a dx because you're familiar with integrals that have a dx in them. But I was afraid that would also be confusing because the way your author used x, he doesn't use it as a variable of integration. So I need something else. So that's the avenue I took. So if that'll be okay, I'm in this integral, and it might be kind of hard. Don't think of x as the variable of integration. I suppose if you wanted to, and make it look a little bit more like your calculus class, and change the width to something you'll feel more comfortable with, a dx, we could change our w's then to an x. But if you do that, please don't leave that as an x because you're going to mix those two. This is just some initial distance away. And so maybe right here, instead, you'll give it some kind of symbol like an L, okay, for some length away to begin with. And if you feel more comfortable with that symbolism, great. But either way, we are going to do an integral where we are adding up over the width, whether we call it a W or whether we call it an X. And I guess it's a little Shakespeare here, right? Rose would smell just as sweet no matter what you called it, right? How does that go? Romeo, Romeo, wherefore art thou, Romeo? Deny thyself, and for Capulet I would no longer be called, because what? It's a rose by any other name would smell as sweet. I guess that's the direct quote. A rose by any other name would smell as sweet. Anyways, I digress here. So we have a limit here, and we're going to go from 0 to the total width A, and you can pick which symbol you like. And since I kind of started going down this road, I'll stay on it and use the W here. And like any integrals, maybe the first thing to do is to say, okay, what are constants in here? And pull those in front of the integration. So mu naught and current I can pull out. 2 pi I can pull out. I'll even do a little bit of math. The a would really be a fraction, so when you not only pulled it out and multiplied it, it would end up down at the bottom, and so you would end up with a dw over an x, treating the x as a constant, over dw. Okay? And this, I think all of this, we really haven't done any math, is the crutch of this problem and the hard part of this problem, realizing conceptually that in order to get the total magnetic field, I'm going to just chop it into a bunch of wires, and then I have to add them up, and that means do calculus, and that means I got to get the appropriate symbols. And if that wasn't hard enough, now we actually have to do the integral. So we still have a hard step here where we've got to actually do this integration. And here is screaming our name for a u sub. And so if we put u as x plus w, then a du is equal to a dw. Now remember, I'm treating x as a constant, and so you might want to do it over here and call u is equal to L plus x. And so du is dx. All right, so if we do that u sub, we get a mu naught I over 2 pi a. And then we have an integral, and in place of the dw, I can put the du. And in place of the x plus w, I can now put a u. And then fortunately, that's one of our standard integrals, not an easy one, but that is the natural log of u. Now, of course, when I switch to variables, I also have to switch my limits. And so when w is equal to 0, the u would just be an x. And then at the very end, where w is equal to a, this would be x plus a. And that kind of makes sense. We're just adding up along the width. So we are adding up these little tiny wires from being a distance of x to the last one being a distance of x plus a. So from x to x plus a. So this would be from x to x plus a. Now let me put a page 1 here because I still got some math. I don't think it'll go into a page 3. But it looks like I have now a mu naught, an I, over 2 pi a. And then this would be the natural log of x plus a minus the natural log of x. I might even take advantage of the properties of logarithms, which is the x plus a over x. And, oh, I think I'm done. Nice, because the general rule is to get an answer. I thought I had a few more steps here, but to get an answer in the variables they've given us. So total current, okay, width of it, a, distance away, x, and width is a. Nice. Very nice. And so, ta-da, I'm done. Now, there is one more step. I was kind of wondering how much I should do here, but I'll go ahead and do it because it does involve some more calculus. But they do say, now test your results. Test to see what you get in the limit that a goes to 0. In other words, as I said earlier in this video, test it when it becomes just infinitely thin like a wire, and it should then just reduce to our equation for a long straight wire, and the distance away would be x. Okay, so let me take the limit as a goes to 0 of this equation. Mu naught I over 2 pi a, natural log. And if you'll let me simplify this and write it as x over x plus a over x, because then this is the natural log of 1 plus ax. And that's not an easy limit to do. You probably touched on these in your calculus class. And maybe for you guys, maybe I ought to do this. Where am I? We have, let me grab this book here for a moment. This is actually a science book, not a calculus book, but what they've done in this book is they've given an appendix B, and they've done some reminders. In fact, here's the reminder of logarithms. But I just took advantage of this one here, where you have log of a minus log of b. You can write as a quotient. Here's some geometry. But finally, we get to some of our calculus, and I think that's too far. Oh, this is what I want right here. I guess it would be in this book. They'd call it the expansions of them. But you see right here, if you have a natural log of 1 plus or minus something, it's roughly equal to plus or minus that something. It says if x is really small. And I have a feeling that you probably did this in your calculus, but didn't, commit it to memory. So look it up, or I guess redo the calculus. But I think it's better here to look it up, because when you take this limit, as I just showed you, you could think of this, the natural log of 1 plus a little bit, as just equal to the little bit. And then noting that the a's would cancel off, it would work out correctly that in the limit that a goes to 0, we get the equation as if all the current is confined to a wire, so there's I, a distance x away. So, test your result in the limit. Yes, works great. All right. Wow, that was really a hard one. Hope you got at least some of it right when you went through the first time, and then hopefully my explanation makes sense after all this. All right, take care.